In this lecture, we want to look at financial weather derivatives, which are a new financial instrument that economists are looking toward as a mechanism for replacing crop insurance, let's say. But more importantly, they can also be used to address adaptation in climate change. While mitigation is currently the policy on the minds of politicians, adaptation should be a primary response, because despite mitigation policies, atmospheric CO2 continues to rise. For example, global emissions in 2022 were up 120% over those in 2005. Further, China keeps expanding its coal-fired power capacity, and that isn't going to change over the next 2 or 3 decades. Therefore, financial weather derivatives are an excellent instrument for adaptation to climate change. Currently, the primary response to weather events in the agricultural sector consists of crop insurance. Farmers pay a small premium and the government insures them from low yields caused by adverse weather events such as drought or even hail, although hail insurance is often done privately. A farmer receives a payout if her yield falls below her historic average or some regional average yield. So, for example, payouts might begin when yields are 1 standard deviation below historic on-farm or regional average yield. In Canada, for example, payments begin when yields are about 70% below average. But what are some of the problems for crop insurance? The 2 major problems with crop insurance are related to incentives. Lack of information or asymmetric information leads to the problems of adverse selection or hidden information and moral hazard or hidden. So how do we get around problems of moral hazard and adverse selection? Well, one way is to replace crop insurance with financial instruments known as weather derivatives, which are currently traded on the Chicago Mercantile Exchange. These are known as cooling degree days, or CCD, and heating degree days, HDD, and we'll explain those a little later on. For crop purposes, farmers could purchase financial insurance to insure against drought. But historically, they've also used methods of insurance that included things as mixed farming, that is, raising livestock and growing crops at the same time, planting drought-tolerant plants, planting a variety of crops, and using crop rotations. Hail insurance is still provided, but it's done privately. Weather derivatives are designed based on outcomes of weather indexes, which are not traded in other markets. The prime objective is to hedge against volume risk rather than price risk. Price risk can be taken care of in classic commodity price hedges using options, prices, futures markets, and so on. And what you would see there is if their prices fell, then you would lose this area. The producer would lose this amount of area, but if volume fell, it would lose this area here, and of course if both fell, it would lose both areas. So what we're interested in with weather derivatives is the actual amount of production. So where can one buy weather derivatives? Well, one place is to buy a standard contract that's easy to write from the Chicago Mercantile Exchange. The problem is that this carries basis risk, which we'll discuss further below. Precipitation varies too much, even across a local landscape, and temperatures are measured in Calgary, where the product is based. So in other words, we write a weather derivative product on outcomes at Calgary Airport under the Chicago Mercantile Exchange, but these are not helpful for a farm located in Regina. So in other words, precipitation that occurs over a broad landscape may or may not affect one farmer the same as another. Likewise, the temperature measured in Calgary is not helpful to a farm in Regina. Or one can write an over-the-counter product that's written on an index measured locally, even at the farm level. They could set up an instrument right on the farm. These are flexible, but they carry a potential high credit risk where either the holder of the contract or the farmer is unable to meet the obligations of the contract. Weather derivatives are a more recent phenomena. In 1997, the first weather transactions, these were over-the-counter transactions, took place between Enron and Koch Industries. They were based upon some temperature indices to compensate the energy producer in case of a mild winter. In 1998, the first European deals took place between Enron and Scottish Hydroelectric on a similar basis. And in 1999, trading in weather derivatives began on the Chicago Mercantile Exchange, with heating degree days being the only product then available. If we consider the Chicago Mercantile Exchange, we can look at some key dates here for these kind of weather derivatives. In the summer of '99, it launched its first weather derivatives. 10 new U.S. seasonal and 12 new U.S. monthly cities were added, as were 5 monthly and seasonal European cities in 2003. 2004, the change in the tick size occurred and 5 additional U.S. seasonal cities were added. In 2005, 3 new cities were added and 4 European ones, 2 Japanese cities. In 2007, hurricane futures were added, weekly contracts were included, and snowfall futures and options were being traded. Each of these was an attempt to address issues related to climate change. In other words, economic agents, whether farmers or companies or even individuals, could use these kind of products to protect themselves against adverse weather situations. So this is different than insurance. For example, you might be able to insure yourself through a weather derivative regarding rainfall, but you may not be able to insure a rainfall event using a crop insurance kind of instrument. However, the problem is that many of these derivative products could not draw enough traders and were unlisted. Currently, the Chicago Mercantile Exchange offers heating degree day and cooling degree contracts for 8 American cities listed as Vegas, Atlanta, Chicago, Cincinnati, New York, Dallas, Minneapolis, and Sacramento. But you can see that that may not be very helpful for a city such as Pullman, Washington, or Spokane, Washington, which is located in a totally different area. Heating degree days and cumulative average temperature contracts are offered for 2 European cities, London and Amsterdam, which may not help someone living in Berlin, for example. Now, what kind of weather indexes, what types of weather indexes are there? Temperature is the main underlying weather factor for most derivatives. Number of days or hours that temperature in a certain week in late fall is between -5 degrees Celsius and -8 degrees Celsius it can be a weather derivatives, and it's used for grapes that are used in making ice wine. Heating degree days, where heating degree days refers to the number of days when temperatures are below 65 degrees Fahrenheit and space heating services are required. Cooling degree days are the number of days when temperatures are above 65 degrees Fahrenheit and space cooling services are required. Growing degree days. During growing season, the number of days that temperatures are above 5 degrees Celsius and there is enough heat for crop growth. Cumulative average temperature, the cumulative amount of temperature over a period which can be seasonal or monthly. Rainfall, early frost, hail, snowfall, and other types of weather can be used as weather indexes. Clearly, these kind of financial products can cause all kinds of difficulties for traders and for those who are not initiated in the trading business. For example, heating degree day call options can be used to protect against the negative impacts from cold or warm winter on a business. Beverage or ice cream industry can use cooling degree day call or put options to hedge the risk of cool summer. Now, the payoffs are also an important aspect of this. A call option can be claimed when the value of the weather index is above a specified strike value. while a put option can be claimed when the value of the weather index is below a specific or specified value. So you can see here is a put option, and the payout dependent on the weather variable is equal to lambda times K1, where K1 is the strike value and W is the weather index or outcome. So you get this kind of payout if the weather index is less than or equal to K1 and 0 if it is greater. A call option here is worth 0 if the weather outcome or the weather index that's used in the financial instrument is less than the strike value and equal to lambda, where lambda is the tick size, so the dollar value per unit of the weather index, of the weather outcome minus the strike value if the weather index is greater than the strike value. So how do we price a weather derivative? The premium price of an option, for example, is calculated from the expected payoff. In this complicated expression, C is the premium or price, R is a risk-free periodic market interest rate, T is the date the contract is issued, big T is the date the contract is claimed, and the expected payoff is given by the integral term. So let's first understand the integral term. It consists of this payout, this payoff, which we saw in the previous slide, plus this density function, which is the probability density of various weather outcomes. So basically what we're doing is we're integrating under this density function the payoff. So you can think of it as the probability of a payoff time, or the probability of W occurring with the payoff of that related to that particular W. And we take all of the possible occurrences of W and multiply them by the payoff from each of those or associated with each of those occurrences. That gives us the expected payoff, and it's from 0 because W cannot take on negative values to infinity to include or to capture all possible weather outcomes. This part is the part that consists of the date at which the contract is claimed minus the date the contract is issued, and then we discount that for over that period of time. So then how do we calculate heating degree days and cooling degree days? Suppose we wish to calculate the number of heating degree days required for the months of December, January, and February, and let's assume that turns out to be 90 days. Each day the temperature lies below 65 degrees. For each day that the temperature lies below 65 degrees Fahrenheit or around 18 degrees Celsius, we need to heat our home, say. Suppose the temperature on a given day is 58 degrees Fahrenheit. Then we calculate the heating degree days for that day as 65 minus 58, which is 7 HDDS. If the temperature is above 65 degrees Fahrenheit, there's no need for heating services, so HDD equals 0. For each day of the 90 days during the winter months, we determine the heating degree days and sum them to get the total as indicated in this expression below. Now, how does the market then work? Well, an energy company makes money selling fuel to clients for heating purposes. A warm winter means the firm commits to purchase too much fuel and loses money. It wants to offset some of the loss. Suppose that heating degree days are priced at $200 per heating degree day. The firm hopes for 1,000 or more heating degree days next month, but to protect itself against a lower outcome, the energy firm, remember it's selling energy, will sell 1,000 heating degree days today, so this financial instrument it'll sell today to a speculator, receiving $200,000, so $200 times 1,000, paying back the market outcome heating degree days at the end of the month. So if heating degree days are realized, if 500 heating degree days are realized, the company gains $100,000. So $200,000, which it receives, but it pays back 200 times 500. But it loses from too few sales of fuel. So it gains 100,000, but it loses because it doesn't sell enough fuel. If 2,500 heating degree days are realized, the company loses $100,000, but makes up for it in sales of the fuel. Remember, the 2,500, we subtract from it the 2,000. Now, what predictors are used to establish weather derivatives? Some examples are related to agriculture, but they can be applied more broadly. We've already talked about heating degree days and cooling degree days, but there's also growing degree days, GDD. These are the days times temperature greater than 5 degrees Celsius. Precipitation during the growing season, not less than 10 centimeters, or during crucial times during the growing season, say June and July. So in other words, we can create an instrument that is based on how much precipitation or how many days of precipitation during the season that are below 10 centimeters of rainfall. So in other words, maybe a month without any rainfall. 14 consecutive days without rain. Frost before a certain date, or for ice wine, guaranteed number of days of frost within a certain temperature range. We mentioned this one earlier. Rainfall during September that exceeds 5 centimeters and then makes problems for harvesting. You can develop a product for growing degree days, but must use over-the-counter transactions for other forms of insurance. So what are the advantages of weather derivatives? Well, first off, it eliminates the problem of adverse selection or hidden information. Participation by one individual or firm or farm does not affect the premiums that other firms would pay. Rainfall and temperatures are uncorrelated with participation rates. Remember, adverse selection was a problem because in the healthcare sector, for example, those who were young did not purchase any healthcare insurance. So they were selecting because they knew they wouldn't have problems. The other advantage is that weather derivatives eliminate the problem of moral hazard or hidden action. No individual, firm, farm, whatever can influence the weather. The economic agent cannot affect the payout. The payoff structure is independent of actual outcomes. Warmer than expected winter weather, for example, or it doesn't affect it. It doesn't affect the crop yields either. So these financial instruments are free of any problems with adverse selection or moral hazard. The disadvantages of weather derivatives relate to the burn rate and basis risk. So the burn rate is needed because you need to have a basis on which you need a measure that correlates with the event. So historical data can be used to determine the actuarial soundness of insurance schemes. The insurer needs to determine that the premium that must be charged for the weather derivative is such that the company who is doing the insurance is going to get make some money at least, or not lose money all the time. The burn rate ensures that the measure is somehow correlated with the event. So that's what the burn rate refers to. Basis risk, on the other hand, is based on the location for the insurance derivative, or whatever it is, whatever the financial instrument is. So weather stations tend to be scattered across space. Temperature near the location of the agent in question, a farmer or fuel supplier, is relatively stable, but precipitation is not. We can find that a field will get precipitation during one day and the field next to it gets none. How can we determine whether an insurable event requiring a payout has really occurred? There may not be rainfall at the particular location or farm, but there is at the weather station on which the risk is based. So the instrument is based. And we talked about that already when we talked about the Chicago Mercantile Exchange, which has an instrument, a financial instrument, the heating degree days and cooling degree days based on Calgary Airport, but nothing for the farmer in Regina. So what is used for establishing a premium? Consider the example of crop insurance. So high, low, and average temperatures at several weather stations can be used. Precipitation over a period at a number of monitoring sites. The elevation of weather stations, distances to weather stations, crop yields are correlated with the above measures. Other sectors. Are heating degree and cooling degree days adequate? Why are they not being employed more often? What about flood protection? Home insurance does not protect, but homeowners could and should be able to purchase rainfall derivatives. Wildfire protection. You can purchase a derivative based on a dryness measure or on cooling degree days. Just ensure that the measure you use is correlated with the event. So if we model weather variables, we have two methods of doing so. We could use time series or econometrics, or simulation using stochastic processes. This is for daily temperatures. For daily precipitation, we could look at the frequency and the magnitude or distribution of the daily precipitation. As an exercise, students should read section 9.1 of my Ag Policy textbook, Applied Welfare Economics, Trade and Agricultural Policy Analysis. I will make this available to the students. Let's now consider the problem of establishing a baseline for constructing, say, a crop insurance premium, but this applies just as well to determining what and how to price these weather derivatives. Suppose we have a farm here and we want to know, maybe we want an over-the-counter instrument or maybe a crop insurance premium for this farm. And we have weather stations located some distances from the farm. Here we have 7 weather stations. This one here provides only data on precipitation. This one on temperature, precipitation, as do these other ones. And then one only provides information about temperature. So how do we use this to determine a premium, say, for a farm that requests insurance and is located at that particular point? Consider an example where we have 9 weather stations from A to I, and then we add 2 others. So the temperature at the various stations are given by the numbers in this first row. So these are the temperatures at any given time or some average. And this is the distance from, say, the farm or some other point to those weather stations. All right. So now what we want to do is we want to look at what happens when we consider different combinations of these stations. So if we look at the original 9 stations and take a simple average, we get 8.99 degrees Celsius. If we weight the weather stations by their distance, we get 8.55. And if we weight it by distance squared, we get 8.48. Notice that the number has fallen. If we look only at those stations that are within a 100-kilometer radius of the farm in question, we would then leave out D and J. Then we end up with 8.01. If it's weighted by distance, again by 8.25, and then 8.43 of distance squared. If we exclude A, C, and E, which is possible because sometimes weather stations drop out from one year to the next or the data aren't available, we get a simple average of 8.78, 8.1, 8.04. If B, D, and I are excluded, then we get 8.42, 8.43, and 8.92. And if we add J and K, 8.69, 9.69, 10.44, so the numbers go up. In the previous slide, we saw that the premium that would be charged for crop insurance, or how we come up with payoffs with weather derivatives, is highly dependent on the weather stations, their locations, and how far they are from the farm, which constitutes basis risk. In this slide, we want to finish the lecture by looking at crop insurance versus the financial weather product. Crop insurance still requires that the private insurer establish baseline yields for determining premiums on weather station data. So they have to use this weather station data. The cost to the insurer is high because the insurer has to establish a baseline yield, has to monitor, and so on. And the farmer could still shirk, and you get moral hazard. Therefore, very, very few farmers purchase, and very few companies provide crop insurance privately. Crop insurance in North America in particular is the bailiwick of the government. Usually in the US, the federal government. In Canada, both the federal and provincial governments are involved in providing and paying for crop insurance. In both cases, in both countries, crop insurance is highly subsidized. What about financial weather derivatives? Well, you still need to establish future markets for growing degree days, much like you do for heating degree days and cooling degree days. And those markets simply don't exist. So therefore, we are required to rely on over-the-counter trade on specific weather outcomes. These again are provided privately, and attempts for the government to do these have so far failed, or they have not been, there's been very little uptake. So it turns out that because, much like with heating and cooling degree days, you have a lot of basis risk, these financial weather derivatives simply have not panned out so far.